Good afternoon, everyone. Welcome to the Samvaad-Talk series organized by IIIT Bangalore. On behalf of Team Samvaad, I, Amrita, would like to welcome all of you to today's talk by Professor Nikhil, Krishnan M on streaming codes for low latency communication. With today's talk, we are also kickstarting the new Samvaad theme on a roadmap to 5G and beyond communication. Today's session chair is Professor Aarti Yadi, who is a DST Inspire Faculty Fellow at IIIT Bangalore since January 2019. She received both her MTech and PhD degrees from the Department of Electrical Engineering, IIT Bombay, in January 2017. She was a postdoctoral researcher in the Informatics Research Institute of Toulouse, France, from May 2017 to January 2019. Her areas of research include error correcting codes with primary focus on cyclic, LDPC, turbo, and spatially coupled codes. She has also worked extensively on reverse engineering of communication systems, and her current research interests include covert communication, coding for distributed machine learning, and distributed data storage. We would like to thank Professor Aarti for taking her time off her busy schedule and agreeing to chair this session. So over to you, Professor Aarti.
Thank you, Professor Amrita. It gives me a great pleasure to introduce our today's speaker, Professor Nikhil Krishnan. Professor Nikhil Krishnan received his BTech in Electronics and Communication Engineering degree from Amrita School of Engineering, Amritapuri campus, Kerala in 2011. He received both his master's and PhD in Electrical Communication Engineering degrees from Indian Institute of Science, IISc Bangalore in 2013 and 2019 respectively. He was a postdoctoral fellow at the Department of Electrical and Computer Engineering, University of Toronto during 2019 to 2021. He is presently working as an assistant professor at IIIT Bangalore. His current research interests include applications of coding and information theory to problems in distributed computation, distributed storage, and low latency communication. The title of today's talk is Streaming Codes for Low Latency Communication. These streaming codes have applications in audio and video streaming, multiplayer gaming, augmented reality, etc. These codes are also relevant to 5G objective of achieving ultra-reliable low-latency communication. Without any further delay, I would request Professor Nikhil to take the stage. Thank you.
Thank you, Professors Amrita and Aarti. So today, I'll be talking about streaming codes for low-latency communication. So as evident from the title, we'll be basically talking about how we can achieve reliable low latency communication. So I'll go into details of what do I mean by reliable low latency communication in the coming slides. So right now it's just an overview of what we are going to see. So these are some of the existing techniques which enable reliable low latency communication. For example, we have, this need not be low latency communication. These are mostly techniques which enable reliability. So we have automatic repeat request, which is ARQ. So here, basically the idea is that we have the receiver, which is sending some acknowledgements back to the transmitter. And if the packet is not received at the receiver, after some timeout, then the transmitter will be basically reattempting the transmission, right? So the problem with this approach is that, so clearly there is a round trip delay because of the feedback. So often in low delay requiring applications, this may not be ideal. Another approach is packet duplication. So here the idea is that without any feedback, we are trying to replicate our packets. Here the problem is that we are unnecessarily wasting our bandwidth, right? Because we are sending one more extra copy of each packet or two more extra copies of each packet. And other approaches are like raptor codes, MDS convolutional codes. So here the thing is that these codes are mostly designed keeping in mind random erasures. When we are dealing with random erasures as well as burst erasures, it is possible to do better. And then of course we have physical layer forward error correction. And in this talk, we are basically dealing with packet level. So clearly we won't be talking about that part. So basically in this talk, we'll be seeing an added option, which is streaming codes. And in the next slide, I'll informally explain what do I mean by streaming codes. So by streaming codes, what do I mean is that they are packet level codes which are designed to efficiently handle packet erasures. So here I have put quote unquote efficiently. So I'll explain in coming slides what do I mean by efficiently. And also we have a decoding delay constraint in place that also we'll see. And this work of this line of work of streaming codes actually originated at MIT, and it was followed up at University of Toronto and also IISc. So this is an overview of the talk. Initially, I'll be talking about the setting of streaming codes, and I'll be sort of formally explaining what the setting is all about. And in the after that, I'll just give a quick review of error correcting codes, some of the techniques that we'll be using in order to design our codes. And next, then we'll see how our approach is, and then we'll explain how to construct a family of streaming codes. And finally, we'll conclude the talk with an experimental evaluation that we have done. So this is sort of the formal definition of our setting. We have information bearing packets S0, S1, etc. Let's assume for the time being that we have an infinite stream of message packets, but it can be easily generalized to finite streams as well. And this stream of message packets or information bearing packets need to be transmitted from a transmitter over to some receiver. And the channel here is an erasure channel, and owing to reasons such as network congestion, some degraded wireless link, or simply packet arriving too late. So for all these reasons, some of these packets may get dropped from the channel. So essentially we have an erasure happening. Some of the packets are erased. So if you see this figure, each of these rectangles indicate a packet, a transmitted packet. We have 1, 2, 3, 4, 5. And here packet 2 and packet 4 are erased. Those are indicated by shaded rectangles. And the goal here is to use a packet level forward error correction scheme. So that's basically FEC, to ensure the best possible trade-off between rate and reliability. We'll see what do I mean by rate, reliability, etc. And also we have a delay constraint in place, meaning if I have a message packet S of t, which is supposed to be sent at time t, it has to be decoded by time t plus tau. So there is that delay of tau time units. So obviously such a setting has applications in interactive voice and video, multiplayer gaming, AR, VR, and also we can consider the URLLC use case in 5G. There also we have multiple applications. And the commonality that we can see among all these applications is that we have a stream of packets. It can be voice, video, or data. And we need reliable low latency communication. So that's kind of like the common thread which is connecting all these applications. So in order to design a coding scheme, first we need to have a mathematical model of the channel, right? The Gilbert Elliott channel model, the GE channel model, is a widely applied channel model in communication networks traditionally. So we'll begin with what do I mean by a GE channel. So this is actually the description of the GE channel. It's a two-state channel. We have a G state, which is the good state, and we have a B state, which is the bad state. And these are the transition probabilities. So from state G to B, it can move with transition probability alpha, and similarly from here to here, we can move with transition probability beta. And if the channel is in good state, it will act as if it's a packet erasure channel with probability epsilon naught. Okay. And if it is in bad state B, it will act as a packet erasure channel with epsilon 1 erasure probability. So since it's a bad channel, so we assume that epsilon 1 is much larger compared to epsilon naught. Quite often we'll be like taking epsilon 1 to be equal to 1, and epsilon naught will be pretty much close to 0. So if you just see here, this channel is sort of trying to emulate two kinds of erasures. One is random erasures. So if you see a channel is in G state, it's kind of behaving like random erasures. It's behaving like a binary erasure. Yeah, it sort of behaves like a erasure channel. And if it is in B channel, since epsilon 1 is like close to 1, it's sort of behaving like a bursty channel. So we have both these characteristics built into this channel. We have we can have random erasures as well as burst erasures. So we have the channel model here, but the problem with this Gilbert Elliott channel model is that it's not really tractable with respect to designing codes. So we need some sort of an approximation. So now we'll see a tractable approximation for the G channel model. Okay? And here I have put again tractable in quote unquote, and I'll explain in coming slides what do I mean by tractability.
Nikhil, a small doubt here.
Yeah.
Go back your last to last slide.
Sure. Yeah.
If there are more than 2 nodes, what will be the model?
Yeah, that is called a Frischmann channel model, but yeah, in our experience we didn't consider that, but yeah, in some of our theoretical papers we were actually simulating that channel model as well.
Okay, and can you tell me what's the eraser channel? You have already mentioned the eraser channel in earlier slide.
No, erasure channel I didn't really mention. So basically what I mean is that with probability epsilon naught, there can be an erasure. That's it.
When you do, there will be eraser, meaning let's say your bit will be completely lost. Is it?
Yeah, that packet will be completely lost. Since we are dealing at packet level, so I'll be talking about only erasures of packets or receivability of packets. So by PEC of epsilon naught, what I basically mean is that with probability epsilon naught, a packet will be lost.
Okay.
And loss is basically my erasure because we are basically talking about design coding schemes. So losses are naturally visualized as erasures in coding domain. So because of that, I use that terminology. So now we'll see how we can tractably approximate the G channel, and I'll see what do I mean by tractability. We'll see what do I mean by tractability. Okay, so this is the model. It's a pretty simple model. So we have all these parameters. We have a parameter A. We have another parameter B. We have one more parameter W, and then a delay parameter tau. So let's consider this figure. So each of these rectangles, each of these squares are indicating a packet, a transmitted packet. What the model is basically saying is that if we consider a window of W consecutive packets, then there can be either A random erasures, or else there can be a burst of B erasures. So let's consider this example here. So here we have W equal to 5, and so here x of 7 till x of 11, that's like a window of 5 consecutive rounds. And here we have a burst of size 4, which is b equal to 4. And again, if we consider 8 till 12, again we have a burst of length 12. And if you consider 9 till 13, we have a burst of length 3. But that's like a sub case of whatever we are dealing with. So this is like the worst case scenario that I'm talking about. But on the other hand, if we see x of 11 till 15, x of 11 till 15, there we are seeing 2 random erasures, right? And so, yeah, this sliding window channel model is basically dealing with all these sort of erasure patterns. And on top of that, we are also imposing a delay constraint, meaning each of this lowest packet should be recovered with a delay of tau. In this case, it's tau equal to 4. So what we are trying to achieve here is that this particular lowest packet, for example, it needs to be recovered by time 12. So that's basically the BCSW channel model. And now in order to talk about that tractability point, which I mentioned earlier, right? Because we introduced this model as a tractable approximation of the Gilbert Elliott channel model. So in order to bring that connection, let me define 2 things here. So suppose we are considering 6 consecutive slots, okay? And this is a snapshot of 6 consecutive slots. And let's say there's an erasure here and erasure here. By weight, what do I mean is basically the number of erasures happen within this window. So for this particular window, the weight is 2 because we have 2 erasures. And by span, what do I mean is basically the width, okay? The starting point and ending point, that width will measure. So in this case, the span is actually 4. So for any given window of W consecutive rounds, we can measure these parameters, right? The weight and span. Weight indicates the number of erasures happening within that window, and span is basically measuring that width. So having defined span and weight, now let's try to connect to the Gilbert Elliott channel model. So what is going on here is that, so here I have, first of all, I generated a sequence of 0.1 million, 1 lakh instances of Gilbert Elliott channel as per this specification, alpha equal to 10 power minus 4, beta equal to 0.6, epsilon not equal to 0.01, and epsilon 1 equal to 1. And then I try to empirically measure the probabilities. So then I considered all the sliding windows happening within that sequence, and the sequence, and I was actually considering all those sliding windows of width W equal to 6, and then trying to measure span and weight. And here I have listed down the empirical probabilities. Okay, so here we can see that 94.08% of the time I was seeing like no erasures in all those windows. But with this percent, for this percentage of windows, there were like A equal to 1 and B equal to 1, and so on. So here, one thing you can notice is that there are like these rectangles here are not populated, right? Why is that the case? Because clearly from the definition of span and weight, we can see that span is always greater than or equal to weight, right? And because of that reason, we will not be having any entries in this region here. Span cannot be less than or equal to weight. So this region is like completely unpopulated. And when there are like 0 erasures, clearly span and weight will be 0. So that's why there is nothing here. And when A equal to 1, span and weight will be basically 1. And that's why there is nothing here. But starting from here onwards, there can be entries here. And based on this empirical probability, so here I'm considering the sum here to be less than or equal to 10 power minus 5. Okay. So this sum here is actually amounting to less than 10 power minus 5. And because of that reason, if I take my channel parameters to be B equal to 4 and A equal to 3, we can basically account for all these patterns. except this pattern. So by choosing the DCSW model with A equal to 3, B equal to 4, and W equal to 6, we can basically account for 99.99999. There are like 5 nines after the decimal point. So that percentage of erasures are taken care of if you use a G channel with these parameters. So this is the tractability point I was mentioning about. So given a G channel, we can always find A and B so that we can sort of match the channels. And given this deterministic channel, which is the DCSW model, it is much more tractable to, so that we can design efficient coding schemes based on that model. Now I will give a quick review of some points from error correcting codes, which we'll be using when we discuss the construction of our codes. So an NK linear code, it's basically a subspace of FQN having dimension K, and it can be basically represented in terms of a generator matrix, right? So a code, each vector will be referred to as a code word, and each code word will be basically obtained as multiplication of some G, which is of size N by K, with a message vector which is of size K by 1. And the rate of the code is defined to be K by N, because we are mapping a message of length K to a vector of length N. So it's kind of we are sort of expanding the number of symbols, and because of that, the rate is defined to be K over N. It is better if the rate is closer to 1, because that basically means that we are adding smaller and smaller amount of redundancy. And associated with every linear block code, we have a parity check matrix H, and a code word is an element of the code book C, if and only if we have, even only if the code word is satisfying this particular property here, which is matrix multiplication of H and C, that should yield the 0 column. And now let's briefly discuss some recoverability properties that we can see with respect to the parity check matrix. Okay. Let's say we have a code which is of length 7, n equal to 7, and suppose this is the parity check matrix that we have. So here HI indicates a column of the parity check matrix. So we have 7 columns here. And suppose code symbols C0, C2, and C5 are erased. Okay. And these 3 erased symbols can be recovered if and only if the corresponding columns of the parity check matrix form a linearly independent set.
Professor Nikhil, there is a quick question from audience. Why these codes are called linear? I think it will be better if you can answer this question at this moment.
Yeah, sure. So these codes are called linear because if I take any code word, if I scale that with a scalar from the FQ, then that will be a code word in the code book. That's one property. And the other property is that if I take sum of code words, that will also lie in the code book. And because of these two properties, we can say that it's a linear space. Here we were actually discussing some recoverability properties. So by recovery, I mean some symbols, code symbols are lost. I'd like to recover that code symbols using the remaining available symbols. So that's the property I'm talking about. And I'm talking about that with respect to the parity check matrix of the code. Conventionally, when we discuss recoverability, that's often discussed with respect to the generator matrix. But here, our code constructions are basically based on parity check matrix, and that's why I am trying to explain all these recoverability properties with respect to the parity check matrix. Okay, so yeah, here we are assuming that C0, C2, and C5, those code symbols are erased, and I would like to recover those code symbols using C1, C3, C4, and C6. And this is possible if and only if the corresponding columns, that is H0, H2, and H5 of the parity matrix, those form a linearly independent set. So that's this property. And in some cases, I may not want to recover all these symbols. I may be interested in only recovering C0, for example. In such a scenario, what happens is that the criterion will be basically H0 should not lie in the linear span of H2 and H5. So that's basically what I'm noting here. So if you want to recover just C0, that's just one symbol out of these three erased symbols. The property that we want to have for the parity matrix is that H2 and H5 should not span H0. Now let's consider an example just to like. So this is a parity matrix of a 7-4 Hamming code. And let's assume that C0, C2, and C5 are erased. That those corresponding columns are marked in red. And since these three columns are linearly independent, we can basically say that C0, C2, and C5 can be recovered. Okay. But on the other hand, now let's assume C0, C1, C2, and C5 are erased. Okay. And here we basically have some sort of a linear dependence between these columns, the column 1, column 2, and column 5. So here I'm indexing starting from 0. So 1, 2, and 5, those form a linearly dependent set. And because of that, we cannot recover C1, C2, and C5. But on the other hand, if we consider the case of C0, that is actually linearly independent of the remaining columns. So because of that, we can recover, in fact, recover C0, even though all these four symbols are erased. Okay. We'll be again revisiting this property when we are discussing our code construction. So now we'll return back to the streaming code setting. Okay, so we were talking about, initially we were talking about packet erasures, right? So we need to combat packet erasures. So in order to combat packet erasures, we need to introduce redundancy. There are two ways to introduce redundancy. Okay, so we have our message packets here that will pass through some encoder. Okay, we can either introduce additional packets, which we will refer to as parity packets. That's one approach. So we have our message packets here, and in addition, we are generating parity packets, which are functions of these message packets. So that's one approach wherein we are increasing the number of packets, but each packet will be either a message packet or else a parity packet. So this approach we will refer to as parity packet insertion approach. And the other approach is the packet expansion approach. Here the number of packets will remain the same, but what happens is that we'll be appending some parity symbols to each of these message packets. So we'll be expanding the size of each packet, but the number of packets will remain the same. So that's the packet expansion approach. And the code construction that we are discussing can be extended to both these approaches, but we'll be primarily talking only about packet expansion approach in this talk. So now let's formally define what do I mean by rate of a streaming code. Okay. Yeah, since we'll be talking only about packet expansion approach, let's focus our attention to this first part here. Okay. So here, each message packet, let's say it's having size k symbols, and each coded packet is having n symbols. So each coded packet is obtained by appending some parity symbols to each message packet. So clearly n is greater than k, and we are adding n minus k parity symbols to each of those message packets. And the rate here will be basically naturally defined to be k over n. Let's just discard this part of the slide because we won't be talking about parity packet insertion approach in this talk anymore. So this is what we are going to do in order to get a packet level code from a block code. Okay, so suppose we are having a linear block code which is of this form. So if you consider this diagonal here, each colored diagonal represents a code word of some block code. Okay, so here I am assuming k to be 4 and n to be 8. So all these initial symbols are basically message symbols, and the last 4 symbols in each diagonal are basically parity symbols. And we are trying to sort of diagonally embed each of these code words in the packet string. Okay, and here each column indicates a packet, and each diagonal is basically corresponding to a linear block code, and that's basically the idea. And what basically happens here is that now if we look at each column, we can see that the first 4 symbols in each column will be basically message symbols, and the last 4 symbols in each column, that's each coded packet, will be basically parity symbols, which are functions of message packets from previous time slots. So basically we have achieved the packet expansion here using linear block codes. Okay, and this is how we are going to generate our packet level streaming codes. We'll be basically taking a linear block code and we'll be diagonally embedding that code into a packet string to generate the effect of packet expansion. In this example, I have used an 8-4 linear block code, and I basically get a packet of size 8 here, a coded packet of size 8 here, where there are like 4 message symbols in each packet and 4 parity symbols in each packet. So that's basically the structure which we use to generate our code. And now in the remainder of the talk, I'll be talking about how we can generate those block codes which we'll be using in the diagonal embedding scheme so that we can generate the packet level coding scheme. Before going there, I also need to explain about a certain notion of rate optimality. So in order to do that, let's first recall our DCSW channel model. So this was actually the model, right? The model basically covers all erasure patterns which satisfy the following property. In every sliding window of W consecutive rounds, there can be either A random erasure or else B burst, or else a burst of length B, right? That was basically our model. And we wanted to recover each lost packet with a delay of tau. So that was basically our DCSW model. And now we will say a code is said to be reliable for the DCSW channel if it can recover from all admissible erasure patterns. That's basically my AEP. All admissible erasure patterns of the DCSW channel with a decoding delay of tau time units. If that is possible, then we'll say that code is reliable. Okay. It turns out that the rate of any such reliable code is upper bounded by this following expression. So we have sort of complicated looking expression, but it's pretty simple. So here we have a tau effective, which is basically a minimum of W and tau plus 1. But in the remainder of the talk, I'll be basically setting tau effective to be equal to tau, and I'll assume W to be equal to tau plus 1. So basically, for the DCSW channel, we had 4 parameters. So we had the random erasure parameter B, we had the B parameter, just indicating the burst length, we had the window size parameter W, and also the delay parameter tau. We can actually merge the W and tau parameters by setting W to be equal to tau plus 1. There's a reason behind that, but I won't be going into that. So in the remainder of the talk, I'll be basically dealing with only 3 parameters. I'll be having A, B, and also W, which is also equal to tau plus 1. Okay. We have basically 3 parameters. And our goal is to construct coding schemes which can tolerate all erasure patterns which are permitted by this DCSW channel model. And the rate of those coding schemes should match this particular bound here. Okay. Since we are setting W to be equal to tau plus 1, the bound basically becomes tau plus 1 minus A over tau plus 1 plus B minus A. So I am just summarizing what our goal now. So we started off with some Gilbert Elliott channel model, right? And we also have some delay constraint, which is specified by the application that we want our code to apply. And we also have some sort of packet erasure probability requirement from the application, which is PE. And from the G model, we can actually estimate an A, B, a set of parameters, A, B, W, tau, which meets all these requirements, right? As we have discussed earlier. And once we have all these parameters, we'll then design the coding scheme, which is rate optimal and tolerates all admissible erasure patterns permitted by this particular DCSW channel model. So that's the approach that we are going to take. This is just a brief summary of the literature on stringing codes, but in the interest of time, I won't be going into the details. So in the earlier work, it was mostly focusing on burst only code constructions, and then later there were a lot of works which were focusing on simultaneously burst and random erasures. But the initial works, they were not optimal in the sense that the rate was not quite meeting the rate upper bounds, but it was this work which was actually giving the first non-code construction, which was optimal and was also tackling both burst and random erasures. And in this talk, I'll be basically focusing on this particular work. So again, just a quick recap. What we are going to do here is we'll be basically constructing a linear block code, and then we will use the diagonal embedding technique to map those block code to a packet level erasure code in the following manner, right? As we have seen earlier. So here each diagonal is a code word of the linear block code, and each column here is a packet. And let's consider an example in order to see how the code looks. Let's take A to be 5, B to be 8, and tau to be 12. Okay. And in this case, the R optimal is turning out to be 0.5. And we'll be basically considering a code which is having n equal to 16 and k equal to 8, which is matching the rate bound. Right? K over n is 0.5. So now in terms of the scalar block code, these are the requirements that we want, right? So we have A equal to 5, B equal to 8, and tau equal to 12. So let's consider this burst of length B equal to 8. So it's actually raising code symbol C0 till C7. I want to recover C0. Okay. Because of the delay constraint, I can look only till C12. Because my delay constraint is tau is actually 12. And because of that, C13, C14, and C15 are inaccessible. Because of the burst erasure, already C1 till C7 are not available to me. In addition, because of the delay constraint, C13, C14, and C15 are also not available to me. So in order to recover C0, I can basically access only C8, C9, C10, C11, and C12. So that's with respect to recoverability of C0 from burst erasures. Similarly, let's consider one more burst. Let's consider a burst which is starting at C2 and ending at C9. Again, a burst of length B equal to 8. Here, C0 and C1 are known. Okay, and C10 till C14 are non-erased and they are available. But because of the delay constraint, I can go only till 2 plus 12, that's 14, and C15 will be inaccessible because of the delay constraint. But once we begin to look at burst erasure starting from C3 onwards, the delay constraint will not be active because 3 plus 12 is already taking me to the end of the code word, right? 3 plus 12 is 15, so that's already the end of the code word. And from C3 onwards, for any burst, the delay constraint won't be active, and the only inaccessible symbols will be due to the erasures, right? So in this particular case, I am considering a burst erasure which is starting at C6 and ending at C13, and all these symbols are gone. And here I can talk about recovering all these symbols together, C6 till C13. We cannot really talk about recovering all these symbols together in this particular example, right? Because for recovering C0, I could look only till C12, right? But in order to recover C1, I can access C13 as well, but right now I am not considering that, right? So because of that, here I can do only one by one recovery. But as soon as the bursts are within C3 till C15, then I can do sort of group decoding. I can try to recover all these symbols together because the delay constraint is not active there. So that's why I have listed, I have categorized these two recovery properties as two. Whenever the bursts involve symbols C0, C1 or C2, then we can only recover one symbol. And that's basically my B partial recoverability requirement. And if the bursts are like completely within C3 till C15, then the decoding delay constraint is inactive, and those recoverability properties I will be referring to as B full. Analogous requirements can be posed even for random erasures. So here, recall that our A parameter was 5. So we basically want to recover from 5 random erasures. Let's say those 5 erasures involve C0. Again, as in the previous case, we have C0, C3, C4, C7, and C10 erased. Because of the delay constraint, I cannot go further than C12. So C13, C14, and C15 are inaccessible because of the delay constraint. And so basically, I need to recover C0 using all these light shaded symbols. That is C1, C2, C5, C6, C8, C8, C9, C11, and C12. Similarly, if we consider this pattern here, again, delay constraint is active here because 2 plus 12 is 14, and because of the delay constraint, C15 is inaccessible. And I can talk about recovering only C2 here. But as soon as the 5 erasures are within C3 till C15, as in the burst case, the delay constraint will not be active anymore. And now I can talk about recovering all these 5 symbols together, right? In this case, C5, C8, C9, C13, and C14 can be recovered together.
No, we are good. There are no questions yet. Maybe towards the end of the talk, we'll have all the questions.
So far I have listed down some recoverability properties that we want with respect to the code symbols. So now we'll try to map these in terms of the
just Professor Nikhil, I think there is a question from Professor Prasanna. Professor Prasanna, you're not audible. If you would like to post your questions in the chat box, maybe we can ask you.
So far we have discussed some recoverability conditions with respect to the code symbols. Now I'll try to map these requirements with respect to the path-check metrics. Okay. So these slides, the upcoming slides will be basically analogous to whatever we have discussed. Just that we'll be living in the domain of path-check matrices. So yeah. So suppose, yeah, again recall that we are now discussing an example which is A equal to 5, B equal to 8, and tau equal to 12. Suppose we have a burst which is starting from the 0th symbol, C0, and ending at C7. As discussed earlier, because of the delay constraint, we don't have access to C13, C14, and C15, right? Because we have a delay constraint tau equal to 12. And because of the erasures, we don't have access to C1 till C7 as well. So basically using C8 till C12, I have to recover my C0. So that's basically the requirement in terms of code symbols. But in terms of path-check metrics, the corresponding requirement will be as follows. So since these three symbols, C13, C14, and C15 are inaccessible. When we consider the parity check matrix, I'll have to deal with only those parity check equations which don't have any component in those three coordinates. Okay. So let's assume that our parity check matrix is in this beautiful row reduced form such that we have an identity matrix here. Okay. So if this is the case, then we can see that only the top 5 rows of this parity check matrix will be of interest to me, because anyway the last 3 columns are inaccessible because of the delay constraint, and I'm interested in only those parity checks which doesn't have any component on those 3 coordinates, and these 5 rows here are basically a basis for all those parity checks which doesn't have any component on those 3 coordinates. So I'll be basically looking only at the top 5 rows here, okay, because of the delay constraint. And now recall our recoverability property which we discussed initially. So since we want to recover C0 in terms of the parity check matrix, then naturally the requirement will be that this particular column should not lie in the linear span of these 7 columns to the right. So that will basically be my requirement. So these 7 columns should not span this first column here. That is basically my requirement. Now let's consider one more burst, which is starting at C2, for example. Okay. So C2 and it's ending at C9. So all these erase symbols are clearly not accessible to me. And because of the delay constraint, so that will take me to C14 because rho equal to 12. So 2 plus 12 is 14. And because of the delay constraint, I don't have access to C15. The corresponding parity check matrix will be basically given by the top 7 columns of this parity check matrix. I'll be basically removing that last row, which is having a 1 here, 1 component here. And again, analogous to the previous slide, the property that we want is that this particular column here should not lie in the linear span of the 7 columns to the right. But as soon as we enter coordinates C3 onwards, if we are talking about bursts which are starting from C3 onwards, then the delay constraint is like not active. And here we can talk about decoding all these erase symbols together. Say for example, suppose I have a burst which is starting at C6 and ending at 13. Clearly 6 plus 12 is 18, which is like beyond this code. So the delay constraint is basically not active here. And here I can recover all these symbols together. And the corresponding criterion that need to be satisfied by the parity check matrix is that this matrix should be invertible, right? The basic criterion is that all these columns should be linearly independent. And since the number of rows is 8 and number of columns here is also 8, that basically translates to being having a non-circular matrix here. Now let's talk about random erasures. This property is also pretty much analogous to what we have discussed in the case of bursty erasures. Let's say we have a bursty erasures which is involving C0 and 4 more erasures at C3, C4, C7 and C10. Again, because of the delay constraint, I don't have access to 13, 14 and 15. So that basically means that I'll be considering only the top 5 rows of my parity check matrix, which doesn't have any components on those final 3 coordinates. Right? And the requirement is that this particular column should not lie in the linear span of these 4 marked columns here. In this particular example, the delay constraint is not active because 5 plus 12 is 17. So I have already covered the full code word length here. And here I basically have the full parity check matrix at my disposal. And here the requirement is that all these 5 columns should form a linearly independent set, right? Because I need to recover all these symbols together, and that basically means that these particular columns should form a linearly independent set. So these are the properties that need to be satisfied with the Patrick matrix, and now we'll see how we can construct a code which satisfies all these properties. The code will be referred to as a jigsaw code because it's actually built up using multiple segments, which each segment has a role to play with respect to some of these recoverability properties that we have discussed. So in one part, we have basically a matrix, which is satisfying the property that any 5 columns of this matrix are linearly independent. Such a matrix is pretty easy to construct. In fact, this can be seen as a generator matrix of a 13/5 MDS code. So this is one section of the matrix. And then I'll just try to fill in some zeros here. These zeros actually play some role here, especially the zeros in the end. Those are helpful with respect to satisfying our delay constraints. And the zeros here, those are actually helping with respect to the recoverability constraint. If you remember, the recovery constraint was something like, if you have a column here and some columns following that should not span that particular column, right? If we ensure that the matrix is sort of sparse enough, such a constraint is pretty easy to achieve. So these zeros actually help in that regard. And these zeros here will actually help with respect to meeting the delay constraint. And since this column should not be like an odd zero column, clearly we need to have some non-zero element here. So I will put that entry to be 1. It can be a non-zero entry. It can be any non-zero entry for that matter. And we also place some entries here, VIs. These VIs are basically helpful with respect to satisfying the burst recoverability properties. And in our code construction, we basically say that there exist choices of VIs so that all these properties are satisfied, but we don't really explicitly specify how to pick those VIs. And in that sense, our code is non-explicit in nature because all these VIs are not explicitly determined in the construction. We just say that it is possible to find VIs so that all the required properties are satisfied. And here we have some alpha. So here all these elements except alpha are coming from some field FQ, whereas this alpha is coming from some field FQ square. Okay. So I'll explain that in more detail in this slide. So we'll imagine that we have a field FQ square, and we also have a field FQ, which is a subfield of this FQ square field. And all the entries except alpha are strictly coming from within this FQ. And whereas alpha is actually coming from FQ square set minus FQ. So it's actually strictly coming from FQ square, alpha. Okay. And it's not a member of FQ. And that's the way we are picking these alphas. The alpha can be any entry from any element from FQ square, which is not an element of FQ. It can be any element. So now let's go over our code, our Patrick matrix, and see how it is satisfying all our recoverability properties that we want, right? So here I have a burst which is starting at C0 to C7, and the corresponding requirement was that if we construct the corresponding Patrick matrix here, okay. So here I have selected all these rows because these are the rows which are having zeros here. And why am I picking these rows? Because C13, C14, and C15, it's not accessible to me because of the delay constraint. So because of that, I'll be focusing only on those pattern checks, picking only these rows. And now I am selecting only that submatrix which is obtained by picking these selected rectangles here. And this is that pattern check matrix. And now the property that we want to satisfy is that this particular column should not lie in the linear span of these blue columns, right? The orange column should not lie in the linear span of blue columns. And clearly the zeros help. So I was earlier mentioning that zeros in the middle will help with respect to recoverability, right? This is an example for that. Because of those zeros, it's clear that this cannot lie in the linear span of these guys, right? Because clearly alpha is non-zero. And these columns cannot span the orange column. Similarly, let's consider another base which is starting at C2 and ending at C9. The corresponding pattern check matrix is given by this demarcated rows, and I have removed row 3 because it's having one here. It's having a component there at C15, which I cannot really access because of the delay constraint, because 2 plus 12 is 14. So this is inaccessible to me. And once we have selected that submatrix, the property that we want to satisfy is that this orange column should not lie in this span of these blue columns, and that's clearly satisfied, right? That's satisfied because if you look at row 2, we have zeros here, and alpha is clearly non-zero. So clearly, the blue columns cannot span the orange column. So that property is also satisfied. And once we begin to consider burst ratios starting from C3 onwards, then we can talk about recovering all these symbols together. Say, for example, here I am considering C3 till C10. The corresponding recoverability requirement is that this matrix should be invertible, right? The actual requirement is that all these columns should be linearly independent. Since the number of rows is 8 and the number of columns is 8, so that basically means that this particular matrix should be inverted. And VA is basically ensure that that invertibility requirement is satisfied. Similarly, this matrix is invertible. This one is also invertible. This one is also invertible, and so on. That finishes the burst erasure part. And now let's discuss random erasure part. It's also sort of analogous to the burst erasure requirement. And let's say, let's assume that we have a burst erasure which is involving C0, C4, C5, C7, and C11. Because of the delay constraint, we don't have access to these 3 symbols here. And because of that, I'll be considering only this selected part of the pattern check matrix, right? Because these 3 rows, those actually have some component which is involving C3, C14, and C15. So I'll be just throwing away 1, 2, and 3. I'll be looking only at the submatrix. I have selected that submatrix here. And now the property that we want to satisfy is that the blue columns should not span the orange column. And that's actually true here because it's true because of the way we constructed our pattern check matrix. If you look at these last 4 rows, this particular matrix here form a linearly independent set, and because of that, it can never, none of the non-trivial linear combinations of these columns will give a 0, 0, 0, 0 here. And because of that, we can argue that this orange column doesn't lie in the span of these blue columns. And let's consider one more example. So suppose we have all these erasures, C2, C6, C9, C11, and C12. Because of the delay constraint, I'll be throwing row 3 away. And I'll be considering only this pattern check matrix here, which I have selected here. And I want to show that the orange column doesn't lie in the span of blue columns. So in order to see that, let's divide our matrix into 2 parts. Let's look at this bottom 4 rows. Okay. So here, assume to the contrary that the orange column lies in the span of these 4 blue columns. Okay. If that's the case, we basically have some coefficients of linear combinations which are coming from FQ. Okay. Which, when we take that linear combination, I am getting this particular orange column. But on the top, if we consider, on the left, we have some element which is coming from FQ square, strictly from FQ square. But on the right, we have all these elements coming strictly from FQ. Since the coefficients of linear combinations are from FQ, clearly we are having a contradiction here. Because on the RHS, we have some element which is from FQ, and on the LHS, we have some element which is coming strictly from FQ square. And that's basically a contradiction. And because of that, we can basically say that the blue column does not lie in the span of, sorry, the orange column doesn't lie in the span of all these 4 blue columns. But as soon as the random ratios are like within C3 till C15, the delay constraint is not active. In this case, I have my full parity check matrix. I don't have to throw any rows away. And also I can recover all these erased symbols together. And the corresponding requirement is basically that these blue columns should form a linearly independent set. And that is sort of naturally following because of the way we have chosen this matrix here. So since we have chosen this particular matrix here to satisfy this property, right? Any 5 columns are linearly independent. Because of that, this property sort of naturally follows, and that basically finishes the construction. Now let's briefly discuss about an experimental attempt that we have done. So far I have discussed only about all these parameters, right? A, B, W, tau, etc. I didn't really talk about how we can connect this tau, which is actually in terms of time slots, to the actual delay requirement, which will usually be in terms of, let's say, milliseconds, right? For example, B2X requires a delta requirement of at most 100 milliseconds, and telesurgery, which requires a delta requirement of at most 150 milliseconds. And let's say there is a reliability requirement which is at most P. Okay. Now let's say how we can map our tau parameter to such a requirement. Slide is pretty elementary. So this can be naturally done. So let's say we have our source string here, source packet string here. Okay. These rectangles indicate source packet string, and T is basically indicating the inter packet arrival time. So in each T, there will be 1 packet coming. So let's say we have T to be 20 milliseconds. And let's also assume that there's a propagation delay of 40 milliseconds, T, okay? So since each packet send a time slot small t is recovered at time slot T plus tau, in terms of millisecond delay, it basically translates to something like this, right? We basically have P because of the propagation delay, and T because of the interpacket delay, and we have tau plus 1 time slots, right? We are considering the time slot T and the decoding which is happening at time T plus tau. That's basically like tau plus 1 time slots, right? So this will be basically my realized delay, and that delay should be less than or equal to the required delay, delta. And based on this, we can arrive at what our tau needs to be, right? For our example above, let's say our delta requirement was 150 milliseconds, and if t equal to 20 and p equal to 40, tau equal to 4 or lesser will be enough for me, right? If you can ensure tau to be less than or equal to 4, then we'll basically have a delay of 140 milliseconds, which is less than or equal to 150 milliseconds. That's sort of the approach that we will do in order to determine how we pick our tau based on the application. So this is the system architecture that we used in our implementation. At the source, we have 4 threads running. We have a source thread, there's an encoder thread, there is also an adapter thread, and there is also a sender. Similarly, at the decoder also there are 4 threads. There is a destination, there is a FEC decoder, there is an adaptation thread, and also a receiver thread. And the communication is having our UDP. And periodically, the receiver will be estimating the channel parameters and sending back the feedback to the transmitter. But the feedback, what happens is that the feedback will basically consisting only of 2 values. A value, which is estimated based on the packets received at the receiver, and also the B value. So since it will be basically transmitting only A and B, in terms of the communication overhead, it is pretty much negligible. The feedback overhead is pretty much negligible. And the channel model that we have chosen is a Gilbert Elliott channel. So in the next slide, I'll be basically showing a demo. And these are the parameters that we are using for the Gilbert Elliott channel model. Now I'll just play that demo. So here, this video is the actual video, and this one here, it's the uncoded video. Okay, I mean, if you are not using any coding technique, what would be the video at the receiver? That's basically this tile here, and this tile here corresponds to what happens if we use our coding scheme. So in the initial phase of the video, there is some sort of an adaptation happening, and it is not stabilized. So because of that, we are seeing a lot of flickering happening. But towards the end, our code parameters are sort of getting adapted to the channel conditions, and the performance sort of becomes stable. And that's it. So these are some references. Thank you.
Thank you, Professor Nikhil, for a wonderful presentation on streaming codes, and also for sharing your interesting constructions of these streaming codes. It was a very nice presentation.
Thank you.
Now, with virtual claps, I would like to thank our today's speaker. And I would request our audience to ask any questions if they would like to know more about. You can either post your questions or you can unmute yourself so that we can have a better clarity about your questions. Okay, so there is a question from Dibankar, and the question is, where is the channel model implemented in the demo?
You didn't understand the question.
So Dipankar, is your question with respect to the parameters that they have chosen for the demo?
Or is it like how we implemented the channel model?
I guess so. Dipankar, would you like to elaborate your question?
Yeah, I just wanted to know, you mentioned in the you are doing it over a UDP channel.
Yeah.
The transmission. So that's basically, I mean, where did you implement the channel model, so the packet drops and everything?
We actually used some built-in Linux kernel commands. So
okay.
Actually, yeah, had the facility to specify the propagation delay and also Gilbert Elliott channel model as well. So we were basically
on the transmitter side or on the receiver side, where do you?
And also one more thing is that what we did was basically we used a single system and we tried to transmit from one port to another. So it was basically the single system, and we simulated the channel model using Linux kernel commands.
Okay, on the same machine. Okay.
Yeah, within the same machine but different ports.
Okay.
No, thank you, Dibankar. There is one more question from Professor Prasanna. Professor Prasanna, I'm not sure if I understand your question perfectly. His question is about the maximum number of erasures and delay with respect to the code length. And there is another parameter which they would like to know about is the delay of 100 seconds for symbols and erasure of entire block. So, Professor Nikhil, would you like to comment about with respect to these parameters? I'm not sure if I understand this question perfectly. So I think he would like to know more about the maximum number of erasures and the delay with respect to code length. Okay. The question is 1,000 erasures possible to correct? Is it possible to correct 1,000 number of erasures?
Yeah, so basically, if you remember our channel model itself, so it's basically a sliding window model, right? So it is indeed possible to cumulatively correct thousands of erasures, but as long as within each sliding window, the erasures are bounded, sort of. So let's say we have a window of size, say 10, and let's say we can tolerate 5 erasures. So as long as, even though we have like thousands or 10,000s of erasures, but in every sliding window of 10 consecutive rounds, if the number of erasures happen to be less than or equal to 5 or 6 or whatever, then the scheme is going to work. But even if it's otherwise, what's going to happen is that there will be some sort of decoding failure happening in between, but the failure is not going to propagate forever. It won't be catastrophic. So even though in between the channel model is not really matching the actually realized model, that's okay. I mean, locally there might be issues, but globally it's still going to work.
Okay. And Nikhil, I have a question with respect to the code parameters which you have chosen for the construction. So is your code construction generic enough that it can be adapted for any values of say B and tau or the window size W? Or in order to choose the specific MDS code, you have to choose specific parameters for that?
So there are some fundamental requirements that need to be satisfied by the code parameters. For example, A is actually referring to the random erasure correction capability, right? And B is actually referring to the burst erasure correction capability. Because of that, A should always be less than or equal to B, right? Because if the code can correct A erasures, it can always correct a burst of length A, right?
Right.
And because of that, B should always be greater than or equal to A. So that's one requirement. And similarly, we should always have tau to be greater than or equal to tau plus 1 should be greater than or equal to B, because otherwise what would happen is that like a burst starting at some time t, it can actually erase all the packets till time t plus tau. So in that case, we don't have any packet which we can help in decoding the packet which is sent at time t.
Okay, and what about is it can I choose any arbitrary values which satisfy this particular requirement for?
Yeah, so once we have picked A to be less than or equal to B and B to be less than or equal to tau plus 1, then it's feasible to select any parameters. Yeah, but the only caveat is that like the field size is quadratic in delay constraint.
Okay, and I have one more doubt about the way you are considering the actual model with respect to the Gilbert Elliott channel model. So is it does the values that the empirical values that you had shown, do they depend on the parameters of the Gilbert Elliott channel model, like the probability of transitioning from the good to bad state, or they are in general too?
Yeah, so that actually depends on the transition probabilities.
Okay, so if you use the codes that you have constructed by varying some other parameters of Gilbert Elliott channel model, how the performance of your code would be? Do you have any observations towards that?
Yeah, so basically what we need to do is like every time we need to draw the table and find out. I mean,
okay.
parameters which.
And just see how fitting the good.
So actually, in our adaptation, this is what we are doing in essence. At the receiver side, it will be basically keeping track of all these erasures. Okay, let's say in the past m time slots, and then it will analyze window by window how many erasures are happening, what's the span, what's the weight, etc. And then it will try to pick parameters such that it can cover like 99.999% of percentage of whatever patterns it has seen. And once it has decided those A and B estimates, it will send that back to the transmitter, and the transmitter will begin its encoding based on these parameters. And that's what is basically happening.
Okay.
So that estimation is happening at the receiver, and it is basically sending to transmitter the estimated values of A and B, which the encoder is going to use while encoding.
Okay. I would like to request our audience if there are any questions.
Hi, Professor Nikhil. Amrita here. So I have a quick question. Is there any kind of a time analysis which you have done in terms of, the accuracy versus delay trade-off, something like that?
No.
Okay. So would it be relevant in a problem like this?
Yes, really. Yeah, it will be relevant.
Okay. Thank you. That's all I had from my side. Professor Aarti, over to you.
Yeah, thanks, Amrita. I think we'll wait for a couple of seconds if there are any questions. Okay, if there are no more questions, I would like to again thank Professor Nikhil for a wonderful presentation. And with this, I think we can conclude our today's session. Over to you, Amrita. Thanks.
Thank you, everyone, for joining in for today's Samvaad-Talk. Thank you, Professor Nikhil, for a wonderful talk on an upcoming topic related to streaming codes for low latency communication. I would also like to once again thank Professor Aarti for her valuable inputs and for moderating the session throughout. With this, we would like to close the session for today. And I would like to make a quick announcement for the next Samvaad-Talk on the same theme, which is a roadmap to 5G and beyond communication, which will be delivered by Professor Prem Singh on physical layer processing techniques for 5G base station system design. So looking forward to participation of all faculty, colleagues, and students therein. Thank you so much and have a nice day, everyone. Thank you.